Hi, it's Bruce again. Welcome to my Colorado Rocky Mountain lab. And what I've got for demonstration today is a Kemo type VBF-8. It's a dual variable filter. This particular one is an elliptic filter with 90 decibel per octave of change um, in output. The frequency is selectable to 1 decimal place, 3 places. So we get tens, units, and then tenths of a hertz. And the hertzes are selectable in either high pass or low pass um, configuration and can go from 0 to thousands of hertz. So we cover a range of 0.01 hertz to 100 kilohertz with this filter. It's you can use the dual filters individually, putting them into the discrete setting and then taking the output. So I could have a high pass or a low pass filter that is frequency selectable. I can go AC or DC connection. I can have times 1 or times 10 gain. I've got a little peak signal voltage output right here. I can put myself in a normal response or a pulse response. Not something that I'm particularly familiar with, the pulse idea, but it's covered in specifications. And then I can select it to have the filter in or out of circuit, so I can take a look at before and after. Then I can take myself from discrete to series, where I can feed the output of one of the filters into the input of the other and then take the output out, in which case I can create a bandpass filter for anything between 0 and 100 kilohertz. Let me mention that this Kemo has been a reputable, commonplace piece of equipment in very high-end institutions where they were doing studies on anything to do with frequency within that frequency range. So I mean, I've seen studies where they were listening to the sounds produced by ants, or something to do with arterial sounds. They would zero in on the frequency that they wanted, and maybe pass that frequency through, but eliminate all the other surrounding frequencies using this thing, and then just focus on the area of interest. Physics laboratories, it'd be schools like MIT and so on, would be seen using these. The unit's made in England. This was Beckingham, Kent. They're still made. They are, I think, in their, I don't know, fifth revision of the unit, but they still sell them. And we're going to take a look at its operation here and just kind of get a feel for what it does and that it works. Okay, right now I have this thing connected up to this sweep generator. I am sweeping a frequency from, I'd say about 100 hertz or less, up to more than a kilohertz. And I'm sweeping it probably somewhere in like 10 to 20 times a second, something like that. And then displaying the output on the oscilloscope up here. So what we see there is the envelope of the sweep as it goes within that range of frequencies that we're set to right now. And what is that? Well, we have a high-pass filter that we're going into that will pass everything that is greater than 10 times 100, so be 1,000 hertz. But we are connected in series, and we have the other unit that's in series with it connected as a low-pass filter that will reject everything that is over 13 times 10 squared, so 1,300. So we've got to be greater than 1,000, but less than 1,300 at the moment. And that's what we see up on the screen up there. When the sweep generator gets within that frequency range, you see the envelope where the center frequency would be effectively the center between 1,000 and 1,300, so about 1,150, something like that. And I can let you listen to that by turning up the volume on this little signal tracer. Okay. So that's what that sounds like at that sweep rate. But the thing about it is you are hearing probably more the effect of the sweep rate right now, and it's 20 times a second or whatever, delivering a pulse of sound, and you're not really getting the true sound that's within the envelope. So what I'm going to do is I'm going to turn the sweep rate down, and we're going to listen to the change. There we go. So that's the sweep of the generator between 1,000 and 1,300 hertz, heard at a slow repetition, giving us time to actually hear the signal in between the on and off. And as I turn it up, it becomes more of a blip, and really it's the timing of the sweep that we hear more than we hear the signal in between. However, we can still see on the screen the effect of the sweep, and we see the frequency in between. There we go. So that's connected as a band pass. We are allowing the signals that are within those two frequencies to pass through, rejecting all others. Okay, so here I put myself in the parallel mode, and I have a high pass filter that's allowing anything over 4,000 hertz to go through without rejection, and then we have the second channel set up as a low pass filter, and it's allowing anything 3,000 hertz and under to pass. So what do we see on the screen up here? Well, let's see if we can get this thing to lock in. There we go. What we see is that anything 4,000 and up is going past, and anything 3,000 and lower. So we see a notch filter. We're not allowing the frequencies within 3,000 and 4,000 to go through without being reduced. So you get that notch. When you're set up as a notch filter, then the focal point of the notch, which is the dead point, is the frequency that you're trying to eliminate. So right now we've got this thing set up so that we're eliminating roughly a 5 kilohertz tone. If we look at the signal on the scope, and if we listen to the signal that's being produced out of the audio generator, or the signal tracer, as I reduce my frequency, you can hear the amplitude increase, or as I increase my frequency, get back to the 5 kilohertz point, it almost disappears. And then you hear as we pass it and we start to go up in frequency, it comes back again. So that's an example of a notch filter. You knock out a signal that you don't want to hear. Oh, a case like that might be, let's say you're listening to a radio broadcast and there is a squeal in the broadcast that you don't want to hear. You could tune this thing into that squeal and knock it right out, and the broadcast to be listenable. So that's an example. Well, if you're interested in studying vibration analysis, certain types of equipment would produce vibrations that are very, very low. Maybe another thing would be earthquakes. You want to try and analyze the vibration of something that might be sub a hertz anyway. Here's an example of actually being able to measure that. I mean, I've got right now, I'm producing a frequency of 0.145. Why am I doing that? Well, I've got this Kemo variable filter set up here, and I have it set up so I have a high pass and a low pass filter in series, and I am passing frequencies that are greater than 0.1 hertz but are less than 0.19 hertz, and the average of that's about 1.45. And what I'm seeing up here is that slowly moving dot on the screen. I am at 0.5 volts per division, so we are going up and down approximately 1.5 volts. So this is 3 volts peak to peak that I am seeing, and I am working at a frequency of about 0.145. So 145, that's what I dialed in. So okay, show me that that means anything to me. Well, let's say we tried to go to a tenth of a hertz more. What would happen? So I'm going to raise it right now, and what we're going to see is that our resonance is going to dampen and we'll start to flatten out. Alright, there we have, we've flattened out. Well, that's a tenth high. Let's go back to 0.145 and we should see ourselves come back into resonance. Yeah, we see it starting to swing. There we are. We're back into resonance. Now I'm going to drop myself a tenth of a hertz. So now we're at 0.45 hertz. And once again, we should see ourselves dampen and begin to go flat. And we see it happening. There we go. And if I go back again to 0.145 by adding a tenth, I'm going to see myself come right back into resonance again. So I could bandpass 0.145. I've measured it. I've adjusted myself. I know I'm capable of passing it. I'm getting plus or minus 3 volt peak to peak, plus or minus 1.5 volts peak, and we're going 3 volts peak to peak. and that's something that I could amplify and study. So, I mean, it's just opens the door. I don't know. Maybe you're studying whales and their vocal habits, or could be sound produced by wind shifts or waves, or sea waves, something like that. Fascinating that it works, though, huh? This Kemo is quite a unit. So there you have it. We have an attractive and very sophisticated filter unit. Actually, two units in one. And it works very well, has a lot of capability, um, very sophisticated. Nice looking, too. So thank you for listening, and happy bidding. Bye.